word? That wasn't from you, was it?
No.
Okay. I thought maybe you sent something. Oh, that was actually your mother paying with PayPal. So, what do you got? What are we doing?
So we've moved on to integration now.
Okay.
And I feel like I have a pretty good understanding of it, but the stuff that's been really hard for me lately has been the substitution rule.
Okay. Cool.
Yeah, we spent about
I say cool because that's one of the things I understand well. There's other subjects in second semester calculus that I might have to turn to my book. But substitution I have a pretty good feel for. So you have some specific problems that you need to integrate by substitution?
Yes.
Let's have them.
All right, I got one here. So it's 3x to the fifth over the square root of 7 minus 9x to the sixth, and that's all under the square root.
Like that?
Yep, just like that.
All right. One of the things you look for in substitution is if the derivative of one is the same order of magnitude as the other. You'll notice that the derivative of the bottom part of the polynomial is 54x to the fifth.
Okay.
So that's what you look for. In other words, you're always looking for the derivative. Now, let me think about this for a minute. So, if I were to let u equal 7 minus 9x to the sixth power, then du dx is minus 54x to the fifth power. And that makes dx equal du divided by minus 54x to the fifth. So the name of the game is, can I write this as a function or as an integral in u? Well, it looks like I can. In other words, I'm going to write it out in full for the moment. You with me?
I think so. How did you decide that to use 7 minus 9x to the sixth for u?
Because this is the derivative of that. It's the same order of magnitude. It's x to the fifth. That's what I care about. Let's go ahead and finish this because I may do it slightly different than they teach you, and I'll go back and I'll show you what the differences are. But I think let me kind of finish it here. So this is dx, and I have to substitute that also. So that becomes du over minus 54x to the fifth. And now look at what magic happens. That cancels with that.
Okay.
And now I end up with du over, what is that, 18 minus 18 u to the 1/2 du. Oops, already got the du in there. Now I can do that. That's an integral that's all in u, and I can solve it using the power rule. And then when I'm done, go back and substitute for u. U is actually this. Okay, so let's finish it. First, let me write it like this: minus 1/18 u to the negative 1/2. So that becomes minus 1/18. Let's see if I add 1 and divide by the new thing, that is u to the 1/2 times 2. I think I did that right. It's been a little bit of time since I've done calculus, but plus c, and then u, we know what that is. So when I go to put the whole thing back into a function of x, there's your answer. Now, you could prove that by taking the derivative of that answer and making sure that what you end up with is what you started with. In other words, this whole thing right there. If I take the derivative of that answer, applying the chain rule and product or power rule, I'm going to get back to that answer perfectly. Because notice that I'm going to have to multiply it by the derivative of the inside. And the derivative of the inside is that minus 54x to the 5th. Divide that by 9, and you should get back to that. Unless I made a math error, which is always possible. But here's what you want is the product you know, the best way to explain it may just be to do another one.
Okay.
Because there are a couple of methods that substitution can be used. That's only one of them. That's where that was the case where you have a composite function where the derivative of part of the composite function was being multiplied by that. And that's what you look for your U-Substitution. Try another one. Most of them are going to fit that, although that, I wouldn't say that was terribly difficult. Oh, let's back up a second on this, because your teacher, I may have done a extra step that your teacher would not do. Okay, this part over here, that is really important to do when you're doing these. Okay?
Okay.
Now notice when I went from this step to that step, I did a couple of things at once. I multiplied both sides by dx, and I divided both sides by minus 54x to the 5th.
Yeah, I think I got that.
Okay. Well, what the schools tend to do is they don't divide by that. They leave that up here, minus 54 x to the 5th, and then they look for that to substitute du for. And I can do that as long as I take out of there a minus 18. In other words, if I factor out a minus 18 from du, I get exactly 3x to the 5th dx. And that's what I substitute for du. But that is kind of like skipping a step, which is fine, and that's what the schools teach you to do, is get it to there. But I think it's actually a little more understandable if you do it the way I did it the first time, where you actually solve for dx, because it's dx that you're substituting for. You have to substitute for that dx. And you're going to substitute du either times something or over something.
Right.
All right, let's do another one.
All right, this one is x over x minus 15.
Okay, this one is a little different. This is not a composite function times the derivative of the inside. Okay? This is one where notice that if I had this, be no problem, right?
Mm-hmm.
Because I could split it up into the integral of 1 minus the integral of 15 over x. I can do both of those easily. Where it's a problem is when you have two terms in the denominator and only one in top, which is the problem we have. Okay? And that requires, let me start it again from scratch. Was x plus 15, right?
Yes, or minus 15.
All right, so look what happens if I let u equal x minus 15. Now, that means x is equal to u plus 15.
Mm-hmm.
Furthermore, du equals dx. Okay? Now look what happens to this integral when I turn it into an integral in u. The top becomes u plus 15, that was x. The bottom becomes u, and it's now du. Well, that's easy to do. In the same way that I did this one up here. I can split this into two fractions and then just use the power rule. Let's do it. So that is equal to the integral of 1 du, that's this part, plus the integral of 15 u, I'm going to put 15 over u du, that's this part. Okay, so that's it. That's equal to u, that's the integral of 1. And this is 15 natural log of u, which is the integral of that. Now, plus c. Now I go back and resubstitute, because you always want your answer to be an x. So this becomes x minus 15 plus 15 natural log of x minus 15 plus c. There's your answer.
Okay.
Now, both of these methods were really different, but these are the main two methods that you're going to use U-Substitution for.
Okay. So for this method, do you always substitute u for the...
Your goal is to turn the denominator into a single term.
So you always use the whole denominator for u?
Yes.
Okay.
Because that turns it into this, And that single term u in the denominator allows me to split the fraction and integrate both parts.
Okay. And that 15, where you integrated 15 over u, and you got
Natural log of u.
yeah, that's just something you have to have memorized, right?
Yeah, the integral of 1 over u is natural log of u. Yeah, that's, and here, let me help you memorize that. You can't use the power rule on that. In other words, if I have this, I can use the power rule, right? Add 1 to the exponent, divide by the new exponent. But if I have this, add 1 to the exponent, divide by the new exponent, big problems. So remember that is unique. You cannot solve that using the power rule. That is the only power that you cannot solve by the power rule. That's the one that's reserved natural log of u is the answer. Or if you think back to your differential calculus, remember that they taught you to memorize that the derivative of natural log of u is 1 over u. And integration is just the inverse of differentiation. Whenever you integrate something, you better be able to differentiate it and get back to what you started with.
Right. Are there any other ones you have to memorize like that?
I don't think so. Those are the biggest thing that the natural logs can be a little tricky. And I'll tell you why. Let's see. Let's say I had something like notice what I'm looking at. Yeah, I could actually multiply this out and then just differentiate it. So let's do this. Okay.
Okay.
Now I can't do that. In other words, now I cannot distribute the x to the third and turn it into one big polynomial. What I should notice is that the derivative of that part of that composite function is that.
Okay.
That means that this should be u right there. Because the derivative of u is always going to end up being in the denominator, and it will cancel out the x's when I go to turn it into, in other words, let's just do this one. I'm going to let u equal x to the fourth over 4 plus 7. Now, since this is a composite problem, I am going to use the trick. In other words, I know I have to differentiate that immediately. It's not a trick, but so now here's where, if you like, I can do it like this. I'm going to take the shortcut this time. Okay, see how I got to that step?
Yes.
Now, notice that I've got x to the third there, and I've got a dx over here. And they are basically next to one another. In other words, I could switch these two if I wanted to. So I've got my x to the third dx. There's my x to the third dx. I'm going to substitute that du. You with me?
I think so.
And all of this is u. So I've done, remember your goal here is to turn it into an integral of u, not x. You can't have any x's left. In other words, when you integrate something that is a function of u, du, if you have x's in there, you're not going to be able to integrate it.
Right.
You've got to be able to get rid of all the x's and convert your dx to a du. And now, if I had gone one step further here, I would have said, okay, that makes dx equal du divided by x to the third. And now I'm going to rewrite this thing as x to the third, u to the 1/2, and then dx, I'm going to substitute du divided by x to the third. This identity right there. And now that works because my x to the thirds cancel. Now I just have the integral of u to the 1/2 du. I can use the power rule, retranslate, integrate it easily.
Okay.
So the key is, this is the primary thing you're going to use U-Substitution for. And that is when you're looking at a composite function, which is this part right here, because it's to the 1/2 power. So it's actually this whole thing is the composite function being multiplied by the derivative of the composite function. Not by the whole derivative of it, but the derivative of the inside of it. And that's what it is. And if it's not exactly the derivative, then you can always factor out a constant. Let's say that that was just x to the fourth and it wasn't x to the fourth over 4. Well, now the derivative is 4x to the third, and I'm only looking at an x to the third. That's fine. What's important is the power of the x is now to the third. I can handle constants. You can bring constants out. In other words, if I need that to say 4x to the third, I'll put a 4 there and a 1/4 there. Now I haven't changed it, and now there's my 4x to the third, and that's going to be the derivative of the inside. So it'll be completely taken care of. But that is the secret, is to get rid of your x's as you try to turn it into an integral in u.
All right. I think I understand that.
If you could do one, we'd prove it. Do you have another one? I can make one up, but I'd rather you give it to me.
Just 1 second.
Like I said, it gets one level a little bit more complicated when you're dealing with natural log functions, because then you want the derivative to be in the denominator, not the numerator.
Right.
And that's a little confusing until you actually do a problem.
Yeah.
I think I can make one of those up. Let me think for a second. Natural log of x squared plus 1 all divided by 2x dx. Okay?
Okay.
Now, normally the inside is going to be x squared plus 1. That's what I'm going to let u equal to. But normally I would want this 2x to be multiplying. But because it's natural log, it's going to go in the other way. In other words, I don't want to use natural log. Darn. I don't think this is the problem I'm looking for. Maybe.
Okay.
Maybe. Hold on. Let's just try it. So u is going to be x squared plus 1. Now always differentiate this. du dx is going to be 2x, which makes du equal 2x dx, which makes dx be d. No, this is not the example I was looking for.
Okay.
This would have worked if that 2x would have been up here. I can't think up a problem where it needs to be in the denominator. This is not it, but it's close. No, I don't know. What do you got? What other type problems do you have?
X over the square root of x plus 2.
Like that?
Yes.
Okay. Is this going to be the first type or the second type?
First type?
No. The first type requires that the derivative of u be on the other side of the fraction bar. And that's not what we're looking at here. In other words, this is going to be the second type. I'm going to let u equal x plus 2. But what that means is, first of all, du equals dx, but it also means x equals u minus 2. You with me?
Mm-hmm.
Okay. So now, can I turn this thing into an integral in u alone? Well, let's see. The x is equal to u minus 2. When you think substitution, that's what you're trying to do, is substitute everything. This is the square root of u, correct?
Right.
And that's du. Now, I've got that same problem where I can split it up into two fractions and integrate two different integrals using just the power rule.
Okay.
You see?
So when
I'm going
you
to
do
this. You want me to finish it?
Sure.
Okay. So what this is equal to, the left part of this fraction is u divided by u to the 1/2. That's u to the 1/2. And the right side is 2u to the minus 1/2 du. With me?
Yeah.
If ever you don't understand what I did, stop me.
Okay.
Well, this is pretty easy. That's just u. I add 1 to the exponent, divide by that, same as multiplying by 2/3. This one is I add 1 to the exponent, divide by 1/2, same as multiplying by 2. Now I go back in and I resubstitute. What was u? U was x plus 2.
Mm-hmm.
So the final answer is 2/3 x plus 2 to the 3/2 minus 4 x plus 2 to the 1/2. All of it's in x.
Okay.
And that's the only way I know how to do that problem. I don't know of a different way. Because like I said, when you have when you start out the problem and you have two terms in the denominator, you can't split that fraction up. When you have x over x plus 1, you got to use this technique. If you have x plus 1 over x, I can integrate that directly. Don't need to use U-Substitution. But make it this, and I cannot.
Right.
I got to use U-Substitution to do that one.
Okay.
What else you got, Chris?
Let me go to a little bit of a harder section.
I can give you one.
Okay.
This is a pretty good one, actually. Problem is actually the tangent. So I'll do the first step for you. If you're integrating the tan of x, well, tan is sine over cosine. Okay? Now, which one do you let be u? In other words, we've got our basic definition, which is that one side of this fraction is the derivative of the other side. But it matters which one you let be u. Let's try it both ways. If I let u be sine x, then du dx equals cosine x. So du would be cosine x dx, and dx would be du divided by cosine x.
Okay.
Well, if I try, here's what I end up with. Sine x over cosine squared x dx. Now, I've done it, but I don't know how to integrate that any more than I knew how to integrate that. Notice what happens if I let u be the denominator. Oh man, I gotta fix this thing so I can figure out how to erase it. I'm gonna go down the middle column. I'm gonna let u be the denominator this time. Now du dx equals minus sine x, which makes dx equal du divided by minus sine x. Now, when I substitute, there's my sine x in the numerator. My cosine x is u. And for dx, that's this. So it's du over minus sine x. And now bingo. And I'm left with nothing but u. So now I can integrate that. That becomes minus natural log, and u was cosine of x plus c. There's your answer.
Okay, that makes sense.
The key, when you're trying to figure out what to make u, you know that whatever you make u, the derivative ends up in the denominator. So if I let the bottom be u, well, the derivative of cosine is sine, and I want it in the denominator, so it'll cancel out that sine of x. Whereas if I let u be in the numerator, the derivative ends up in the denominator. I don't want it down there. I want to be able to take out the thing that I'm not letting u be. This is kind of a classic one. This is one they frequently will stick in your textbook. Do you even have a textbook, or you get everything online?
It's pretty much all online.
Okay. But this one here, you can remember that you have to do U-substitution. It's hard to remember which one you make u. but it's all you got to do is trial and error. There's only two choices, and the first one doesn't get you anywhere. The first
Right.
one gets you to there. Remember, you're trying to turn the whole thing into an integral in U. You got to get rid of all x's.
Mm-hmm.
And if you try again and let that be U, then it works out perfect. All right, go ahead and find me a harder one from your material here.
Okay, just a sec.
Hopefully I'll be able to do it. The good news, actually it's the bad news. The bad news is that U-Substitution, this is one of the easier methods there is.
Oh, really?
In fact, probably the easiest after you get past the power rule. Yeah,
Mm-hmm.
that's the first thing they teach you after the power rule on integration is this
Yeah.
substitution. Everything following this is tougher. Now, how much of that you'll get this year, I'm not sure. They may not go much past U-Substitution. There are at least 5 more methods of integration. Each
Mm-hmm.
one is tougher than the other. There is integration by partial fractions. That's brutal. And then there is integration by trig substitution. You never seen anything so hard. There's integration by approximation using infinite series. That took me 4 weeks just to read one chapter 4 times so I could understand it. So integration is not like differentiation. Differentiation, you got those 4 rules. Power rule, product rule, quotient rule, chain rule, and you can differentiate any function you want to look at using those 4 rules.
Mm-hmm.
Not so with integration. And then there are some functions that there is no antiderivative for, like
Right.
this one right here. There is no function in the universe whose derivative is that.
Mm-hmm.
So how are you going to integrate this? In other words, I can't find an antiderivative for this. So what you have to do is you have to approximate that function using infinite series and then integrate each term of the infinite series.
Mm-hmm.
That's the only way to integrate. No other way. There's no exact integration. Most things you would expect, in the year 2018, that you could have an exact answer on the integral of any formula, and not the case. The best you can do here is an approximation. It's kind of like saying, round off pi to 8 places. And in fact, that is the way they define pi, is by an infinite series approximation. There are
Right.
some infinite series where if you take the first 4 terms, they give you pi to 9 decimal places accuracy. It's rather amazing. I mean, haven't you
Mm-hmm.
ever wondered how they came up with, how do you come up with pi to 25,000 decimal places? Certainly don't take a circle and divide it by its diameter and come up with pi to 25,000 decimal places. But they can do it, but the way they do it is with these infinite series.
Right.
Which is, that's more of a Calc BC. I don't think you're going to get into a lot of that stuff. You're a senior?
Yeah.
Okay. And this is just Calc AB, correct?
Yes.
Is it AP Calc or just regular Calc AB?
Just regular.
Okay, well then you're probably not going to face all of those harder techniques. The fact that you're doing U-Substitution at the end of February, you may do partial fractions. They may do those next. Those are
I
fun.
hope not.
Actually, partial fractions really aren't hard. You just have to learn the method of doing them.
Mm-hmm.
And that can be complicated, depending on the complexity of the function, that can be fairly complicated. All right, you gonna give me one?
Yeah. This one was pretty hard for me. So it's e to the x minus e to the negative x over e to the x plus e to the negative x.
Well, let's take a gander at what we would let u equal. Thinking back to my sine over cosine, what was the best thing to let u equal, the denominator or the numerator?
The denominator.
Right, so let's try that here. And instantly, I can see that the derivative of this thing is my numerator. That's good, right?
Mm-hmm.
In other words, du dx is e to the x minus e to the minus x.
How is that?
Well, if I want to differentiate this, I'm going to use the chain rule. So the derivative of that is e to the minus x times the derivative of the inside, which is minus 1.
Okay.
Same way that e to the 3x, if I differentiate that, I get e to the 3x times the derivative of the inside using the chain rule times 3.
Right, okay.
Okay? So the derivative of my u is my denominator, or my numerator. And I know that when I do my arithmetic here, notice that I'm going to multiply both sides by dx, like that. And then I'm going to divide both sides by that. So that always ends up in the bottom.
Mm-hmm.
Which is perfect because it's going to take out my numerator that I don't want there anymore. I'm turning this thing into entirely a derivative of u. In other words, this now, let me go down a little bit here where I have just a hair worth of writing space. So now I've got this. Here's my numerator, and I always write it out just to show you why it's disappearing. There's that numerator. The bottom is u. And now I have to substitute for dx. Well, dx equals that, which is du over e to the x minus e to the minus x, taking out that which I didn't want there anymore anyway. Now I have du over u. That's just the natural log of u being e to the x plus e to the minus x. There's your answer, plus c. Do you take off points if you forget the plus c?
Not really. I don't think I've ever done that, but I doubt he'd take off points.
Yeah, it's easy to forget. If you're not in a habit of always adding that plus c, and then it gets harder because the next step is when you do definite integrals. And when you're doing a definite integral, there's no plus c.
Mm-hmm.
Evaluate it at 5, evaluate it at 2, subtract the 2, so you don't use a plus c. And so when you've been doing definite integrals for a while and then they give you one that's an indefinite integral, it's easy to forget the plus c.
Yeah.
just remember, what you're looking for here is the derivative of one of these to end up in the denominator. And that's exactly what happened. What I made u, the derivative of that, ended up right here in the denominator, which takes out that numerator. Okay, what else you got?
Okay, so I have the quantity of x to the 3/2 plus 4. That's all to the 7th power. Times the square root of x.
Now notice something immediately. What's the derivative of that?
X to the 1/2.
Exactly. So I have a composite function here, and I have the derivative of the inside of that composite function is right there in my numerator. I know that if I let u be this, then I'm going to end up differentiating that, and it'll get rid of that x to the 1/2. So work me through it all.
So
with that,
u equals x to the 3/2 plus 4.
Always make your next step to differentiate that.
So du over dx.
Oddly enough, in almost every level of integral calculus, your first step is differentiation. Really. In other words, you continue to do all integral problems. Half of them is differentiation.
All right, so that would be 3/2 x to the 1/2. And then multiply both sides by dx.
Now, before we go further, before we do it the way I've been doing it, notice one thing. So I can immediately, if I want to take this 3/2 on the other side, make it right there. Now that x to the 1/2 dx, I'm staring right that in the face. So I can immediately make that 2/3 du. In other words, that became that.
Okay.
You with me?
Yeah.
And then this whole thing is u to the 7th. I have completely gotten rid of my x. Now this is trivial to do. But notice the difference. The way I had been doing this was by solving for dx, which then puts that in the denominator, which is where I want it, so that it'll cancel out that x to the 1/2. But I'm not even going to take that step. I'm going to notice that I've already got an x to the 1/2 dx right there. I'm looking at it. I'm just going to substitute that, whatever that thing is equal to, which in this case is 2/3 du. So it kind of saves a step, but more importantly, this is kind of what they teach. Where do you go to school, Chris?
Arapahoe High School.
Oh, I was there the other day.
Oh, really?
Yeah, I was giving a presentation of ACT seminar at Arapahoe in one of their stadium, their tiered classrooms.
Oh, yeah.
Yeah.
It's kind of near the front.
Yep.
Yeah, I know where
right
that is.
Right near the front. Yeah. Yeah, I had like 23 juniors and seniors were there. I'm not sure how Arapahoe teaches it. Most students prefer this method because it's a little shorter, where you don't actually solve for dx, where you look for something that you see. In other words, I see that in the function, so I'm solving for x to the 1/2 dx. And I have solved for it, so I'm not going to solve for dx. I'm just going to substitute 2/3 du for that x to the 1/2 dx.
Okay.
And I think that's more the standard way it's taught. It's actually a little more understandable if you do it the longer way, because you can see what substitutes where and what gets canceled precisely, a little more easily, I think.
Right.
What else? We got time probably for one more.
All right. Let's see here.
Have they given you any trig? I gave you a trig one, but I don't know if they've given you any.
Yeah, let me see if I can find one.
Okay.
Okay, here's one. Secant squared of x over tangent cubed of x.
That's it?
Yes.
Okay, here's what I'm looking to do. I'm looking to make u something such that the derivative of it is secant squared x. Because I know that the derivative of my u ends up in the denominator. So what am I going to let u be?
Tangent cubed of x?
No, just tangent x. Tangent cubed of x, the derivative of that is not secant squared. Whereas the derivative of just tangent is secant squared. So that means du equals secant squared dx. With me?
Mm-hmm.
That's what I'm looking at. Secant squared dx. So this whole thing becomes du all over u cubed. That's trivial to do. The key is to recognize that whatever you're going to let u be, you want its derivative to be in the numerator. And I know the derivative of tangent is secant squared. That's why I don't let u be tangent cubed. If u was tangent cubed, first of all, the derivative of it would not be secant squared.
Right.
I would have to apply the chain rule and the power rule, and I'd have something a lot more complicated than secant squared. And I would not get rid of the x. The whole goal is to get rid of the x, and usually it's to get rid of the numerator. Like I said, the one time, well, not the one time, but the time it changes is when you're dealing with natural logs, because the derivative of natural log is 1 over x. So then that ends up in the numerator, not the denominator. Gosh, I wish I could think of one. I guess here, I think I can think of one. Let me see if I can make my point in the last 5 minutes here. Let's see. I want u to be natural log of x, and so I want an x in the denominator. Here we go. Now, I don't know how to integrate that. Whenever you have the integral of a quotient with two different types of functions, this a log function and a polynomial, you got problems. Okay?
Mm-hmm.
So if we let u be the numerator, watch what happens. Du dx equals 1 over x. So du equals dx over x. Now I'm going to do it the old way. So now the x ends up in the numerator. So now when I turn this whole thing into an integral of u, I've got u in the numerator. Well, what is dx? Dx is du over, or du times x. I got the x in the denominator. Bingo. That's what I want. I want those to cancel always. And now I've got just the integral of u du, which is u squared over 2, which is natural log squared of x over 2 plus c. Because we were dealing with natural log, that's the one time where it's the reverse. The x you're trying to get rid of needs to be in the denominator, not the numerator. Most of the time, what you're trying to get rid of is going to be in the numerator. Not when you're dealing with something where u is the natural log of x.
Yeah.
Because then that derivative ends up in the numerator, and so you want the other part of it that's going to get canceled out to be in the denominator.
Right.
All right. Chris, this was fun.
I guess, if you want to call it that.
I was worried that you were going to hit me with something that I hadn't done in a year or so, and I was gonna, but I'm pretty good with U-Substitution. Yeah, if you'd have hit me with trig substitution, I'd have said these are the kind of problems you're going to have to send to me in advance. I don't think I can do these in real time.
Right.
But U-Substitution, I'm okay with.
Do you have the same time tomorrow open?
Well, let me have a look. I do. You want that? 6 o'clock?
Yeah, just because we're learning just this last little bit tomorrow, and just maybe go over a couple more of these.
Yeah, no, that's fine.
I gotta take a quiz on Thursday.
Okay. Oh, I love it. Nothing I'd rather do than tutor calculus, especially if I know how to do it. It's not so much fun if I don't know how to do it, but.
And that number you got there is different from the one you texted me on today.
Yeah, that's fine. I've got you in my smartphone, and I always text from my contacts list. So I don't really use that number. Your number is the 720?
Yes, that one's mine.
Okay. I will talk to you tomorrow.
All right. See you then.
All right, Chris. Bye-bye.
Bye.